Welcome to the final session of this particular CCA, the second CCA of the 2014-15 academic year. As with most CCAs, we finish off with a faculty roundtable discussion. Again, a chance to reflect on and talk a little bit about things that we've heard, things that we've thought about, things that we've learned through the last 3 days. So thank you for coming. Again, please feel free to ask questions at the end of this. Well, the way this format works is that we will have each of the four of us will give a few thoughts on the order of 5 to 10 minutes each, and then we'll have opportunity for questions from the audience, which those questions, again, as before, you'll have microphones that will be brought to you. So please, if you do have a question, raise your hand. Someone will come with a microphone, and then feel free to direct your question to any one of the panel members or just to the panel in general, and then we'll pass it around. Okay, and we'll definitely plan to end by 5 o'clock. Okay, first of all, let me introduce myself. My name is Mark Nussbaum. I'm professor and chairman of the chemistry department here at Hillsdale. Also, though, perhaps more to the point, I'm dean of faculty and therefore serve as a moderator for these CCA roundtable sessions. Again, it provides us an opportunity to just think about things we've heard and reflect on them and offer some feedback to one another. So, as you all are aware, the topic of the CCA has been energy and associated issues and controversies. Very timely topic, as it turns out. As many of you may have already seen, there's been news that came out just today about an agreement that was made between President Obama and the Chinese premier to reduce greenhouse gas emissions, well, for the U.S. anyway, pledging to reduce greenhouse gas emissions by 26 to 28% by 2025, which is certainly a more stringent target than had been proposed, at least by U.S. members in the past. Of course, it remains to be seen what will happen with that once it gets to Congress. But again, it just shows that this is a very timely topic. So the week CCA accomplished, as we look back at the variety of speakers that we've had and the talks that have been given, I think it's safe to say that this week's CCA accomplished what Ken Green in his talk said that this panel of speakers would do. That is, we have been educated, infuriated, and entertained, not necessarily in that order. Now, I won't delve into all the topics deeply, but I did want to recall a couple comments that seemed to me of particular interest and just touch on those, and then I'll introduce our other speakers. On Sunday night, Ann McElhaney was entertaining and animated. If you were here, I think there was nobody in the audience that fell asleep. It was very dynamic, entertaining. She was all about what she preached, addressing the culture, getting on Facebook, in the culture's public eye, in movies, chat sessions, selling the story, the political position. Really, I would say she makes a great fracking commercial. And she urges us, in her talk, she urges us to join her. She even says that conservatives need to stop, and I quote, putting our energy into logical arguments and pay more attention to the culture. For a good portion of the audience that heard her, especially those of our guests that are adults, that have been out in the marketplace for a long time, that's a message that resonates and is practical. If the goal is to promote a political agenda, then her approach serves that purpose well. And that's arguably part of the goal of the CCA series. But for our students and faculty, and especially students who are here now, think first that what we are as an institution at Hillsdale College, we are first and foremost an academic institution. Our students need logical arguments, careful consideration of facts to draw well-reasoned conclusions. They aren't in a position, at least not yet, to go out and push an agenda. They are in a position where they should question and learn from multiple perspectives as much as they can about true energy and environmental issues, potential solutions, costs, benefits, and relative risks. We owe it to them to provide forums where quality information representing thoughtful, honest consideration of the facts, reasonable concerns, and options are weighed and considered. And the better we do that, the better they become at pursuing truth and defending liberty. Robert Bryce said he was agnostic whether CO2 is good or bad, but he said, and I quote, I'm tired of the tribalism as far as deciding whose side you're on, us versus them. And I couldn't agree more. I believe he mentioned in his talk 4 R's, and I think on one of the climate change websites there's 3 R's. So in the spirit of keeping with the R's, I'd like to propose my own 3 R's related to the climate change and energy issues conversation. And my 3 R's would simply be respect, reason, and reserve. There are intelligent, moral, thoughtful people on both sides of the climate change discussion. It is unfair and demeaning to label those who disagree with us as bad people, or extremists, or climatists, or deniers, or idiots. Surely we know better. I'm a conservative Christian myself, generally vote Republican, teach at Hillsdale College. Most everybody who knows me would label me conservative, yet I'm also a scientist and a chemist, and I am convinced, as most of my scientific colleagues are, by scientific evidence that there has been unprecedented increase in both global temperature and carbon dioxide concentrations in the atmosphere over the last 200 years. But I will respect those who are unconvinced and are willing to look at the evidence and discuss it rationally. Also, I appreciate Bryce's point. I think he made a very good point when he said that we need to move beyond looking at just reducing emissions and focus also, perhaps more importantly, on the big picture, which includes that, but also includes the need for reliable electricity, economic development, prosperity, and realistic options and risks. No matter what we do, there are no routes that avoid problems and risks, and we need to look at the costs and benefits of all reasonable scenarios. But thank God for those who disagree and challenge along the way, with respect, our thinking. It is by doing so that we sharpen one another and hopefully, in energy terms, generate more light than heat. So, now let me move on to introductions of the remaining speakers of the roundtable. And they'll go in this order, so I'll introduce all 3 of my fellow panelists and then let them go from one to the next. So first, Dr. Ken Hayes, professor of physics and chair of the physics department here. He's been here since 1989. Earned his PhD in physics from Stanford in 1980. He also served as a scientific associate at CERN, 1981 to 1983, and a research associate and staff scientist at the Stanford Linear Accelerator Center, 1983 to 1989. Also, Dr. Kevin Slack, assistant professor in politics, earned his bachelor's from Indiana University in 1999, his MA from UC Davis in 2003, another MA from University of Dallas in 2006, and his PhD from the University of Dallas in 2009. He joined us on the faculty at Hillsdale last year. And then finally, Charles Steele, associate professor of economics at Hillsdale College, holds the Herman and Suzanne Detweiler Chair in Economics. He received his PhD in economics from New York University in 1997. At NYU, he studied under Professor Israel Kirzner, leading scholar of the Austrian school. He has taught economics at the graduate and undergraduate levels in China, Russia, Ukraine, National University, in Kia Moylik Academy, and at the United States, at Montana State University, and of course here. He has also worked as a private consultant on design and review of USDA crop insurance programs. 2012-2013, Steele was a visiting scholar at the Institute for Healthcare Policy, and Aging Research at Rutgers, and he has very recently been appointed to the Board of Policy Advisors of the Heartland Institute. His current teaching here at Hillsdale includes resource economics, history of economic thought, mathematical economics, and Austrian economics. His current areas of research include the economics of healthcare and economics of human trafficking. All right, so let me turn it over then to our first panelist, Dr. Ken Hayes.
I have 10 minutes. And what I'm going to do is I'm going to show you data. I'm not going to show you the results of any climate models. I'm just going to show you data. And the elephant in the room during the whole CCA was, wait a minute, if we burn all these fossil fuels, aren't we going to continue to damage the climate? And the speakers did not address that issue, and so I'm taking it on in this 10 minutes to address that issue. I gave a talk on the physics of the greenhouse effect on campus last Thursday, and I don't have time here to do that talk again. I would like to do that talk again here, but I just don't have the time. So we're just going to look at some data, all right? If you go to Google Images, and I surely hope you can see the graph there, because we're going to see about 10 of them. And if you can't, maybe you want to get up and move closer to the screen. If you go to Google Images and you type in the search phrase, the most famous graph in science, this is what comes up on the top of the list. And that's called the Keeling Curve. Okay, that's the most famous graph in science if by that operational definition as to what comes up in the Google image search. And it shows the carbon dioxide concentration in the atmosphere from 1957 or 1958 when Charles Keeling began measuring the carbon dioxide concentration in the atmosphere on a mountain in Hawaii up until the present time. When he started, the carbon dioxide concentration was about 315 parts per million by volume, and this year we've passed 400. If you look at the general shape of the curve, you see it's growing, and the rate at which it's going up is growing. On top of that, you see these little wiggles, and those little wiggles are the kind of the planet breathing during the seasons, when it takes in carbon dioxide and then releases carbon dioxide. If the northern and southern hemispheres were symmetrical, you wouldn't see it so much, but they're not. Most of the land is in the northern hemisphere, and so most of the land sees winter when the northern hemisphere sees winter. So the bottom line on the numbers is that the current CO2 concentration is 400 parts per million by volume. The pre-industrial value, there's other ways to recover what the CO2 concentration was prior to the time Charles Keeling started to precisely measure it. And before we started major human industry, it was about 280 parts per million. And that represents a 43% increase. You can look in ice cores in Antarctica and see that it has never been this high in the past 800,000 years. This is a graph of the average surface temperature over the Earth for a year. It's the air surface temperature. From about the time we had the Earth sufficiently instrumented with thermometers that you could talk about measuring such a thing. And so we're starting here in this graph from 1880, and we're going up to 2013. And let's see, people usually talk about anomalies, meaning differences from a temperature value. You get more precision if you think of differences in temperatures than trying to come up with the absolute temperature. So all these graphs I'll show you will be in differences. These particular differences are from a base period of 1951 to 1980. So you figure out what the average temperature was in that average from 1951 to 1980 and compare all the other temperatures to that. And if you look, you see the temperature has been increasing. It's been increasing rapidly the last few decades. And over the 20th century, it's gone up by about 0.8 of a degree C. You may wonder, where's 2014 going to appear on that graph? The last data point is 2013. And 2014 is going to be the highest data point on the graph. This is the global temperature anomaly for each month in 2014. And there's 9 months shown. The last month is September. And for 6 of those months, the temperature is an all-time record high. So you can extrapolate the last 7 weeks of 2014, and 2014 will be the all-time record hot year. The last 12 months is the all-time record hot last 12 months, but normally people like to think of from January to December. This is a graph of the temperature anomalies in September, the month of September, over the whole surface of the Earth. And if you look at Michigan there, find Michigan on the map, you can see that Michigan's a little bit cooler than the average. And for the last year, it's turned out that Michigan has been a little bit cooler. The region around Michigan has been a little bit cooler. And we've had a rough winter last year, but the planet as a whole has not. This is the last 50 years of data taken from the Berkeley Earth Surface Temperature Study, and this is my graph. And I analyzed that data to see if I could see any evidence that the rate of warming has slowed down or paused. I've done data analysis for the Particle Data Group since 1984, and I have a lot of experience, and I know how to answer statistically questions like that. And there's no evidence in this graph that there's anything but a linear increase in temperature, general increase in temperature. You can't make a super strong statement with this graph because there's a lot of noise in this graph. You can see that some data points are higher than the linear trend and some are lower. There's a lot of noise in this graph. And that noise is mostly heat being transferred from the atmosphere into the ocean and vice versa. But there are a lot of other measures you can make that have a lot less noise than this. So you can put the hypothesis to the test of whether or not there has been a pause in the warming by looking at some of those other measures. So let me show you some of the other measures. In my presentation last Thursday to the campus, I spent about half of it trying to explain the physics as to why the land really doesn't play a role in determining where the heat goes as the planet's warming. Here's where the heat went from 1971 to 2010, and you see the vast majority of it, like 93% of it, went into the oceans. The land just doesn't play much of a role. A few percent went into melting ice, and a few percent went into the continents, and about 1% went into the atmosphere. So if you want to answer the question with less noise, is the planet still warming? How's the planet warming? Look at the oceans. That's where most of the warming's going. So one way to look at the oceans is to look at the sea level rise. And there's been a series of satellites actually, that since 1992 have been incredibly precisely measuring the average sea level rise of the oceans. So this is a graph from the University of Colorado at Boulder showing the sea level rise from 1992 to 2014. And it has much less noise in it than that previous graph, the average surface temperature graph. And you can see, boy, the trend of the ocean, the sea level rise goes up when the sea level goes up when it warms because of the thermal expansion of water. When you heat water that's above 4 degrees C, it expands. And if you melt ice, and the melted ice that's on land, the water flows into the sea, it goes up. Those are the two largest contributors to the sea level rise. There's also, we've been pumping water from fossil aquifers, and believe it or not, that's measurable in terms of its contribution to sea level rise, and that's a smaller contribution. So there you can see there's no evidence there's any slowdown. The sea's just warming pretty much at a constant rate since 1992. You can also measure the temperature of the ocean. And here's where 3,577 Argo floats are as of today at various places in the ocean. There's a little photograph of one of the Argo floats on the right. And these things for about the last 10 years have been, they go through these 10-day cycles where they drop down to about 2,000 meters, and then they cruise around a little bit, just being carried by the currents, and then they rise up, and they slowly rise up, and they measure the temperature and the salinity and the pressure as they rise up, and they get to the top, they transmit their data via satellite, and they repeat the process. So this is the total ocean heat content measured by Argo in the last 10 years and by previous generation prior to Argo before that and other techniques. And you look at the last 18 years, oceans are warming. There's no evidence at all that there's any pause to the warming. You wouldn't expect to be. You wouldn't expect there to be any pause. I mean, we understand very well what's causing the warming. The greenhouse effect has been understood. First calculation of how much you could expect the Earth's surface temperature to rise if you double the CO2 concentration was done in 1898 by a Swiss chemist who eventually won the Nobel Prize in chemistry. So we've known about it for a long time. There's no mystery here. Here's another data set you could use. There's a beautiful pair of satellites called GRACE, the Gravity Recovery and Climate Experiment, and this is just a beautiful idea. You take these two satellites and they follow one behind the other in orbit, and the distance between them is measured very, very precisely. There's a new generation of this going up in 2017 that'll measure the distance 20 times more precisely than the GRACE satellites. And when they approach a mountain, when they go over a mountain on the on the Earth's surface, the front satellite pulls ahead because it's attracted more strongly to the mountain's gravitational attraction. And then when the rear satellite trailing it catches up, goes over the mountain, it catches back up. And so by measuring that distance very carefully and doing an analysis, you can measure the mass of the mountain. So the mass of the mountain that's called the Greenland ice sheet has been measured very carefully since 2002 when GRACE started collecting science data. And if Greenland wasn't melting, this line would be a horizontal line with some wiggles. If Greenland wasn't melting, this line would be a horizontal line with wiggles. It's measuring the mass loss in Greenland in gigatons, and you can see that the mass loss in Greenland is accelerating. And the precision of the measurement is so good that you can see the difference between summer and winter. You can see, in the winter when the mass of ice grows, and then in the summer when it melts off, you can see those. And you see the rate is accelerating. If you look at the right-hand curve, you can see that the equivalent effect on sea level rise, and it's contributed something like 7 millimeters of sea level rise since they started making these measurements with the GRACE satellite in 2002. Here's the Arctic sea ice. This is the Arctic sea ice volume, measured from 1980. It goes through a big cycle every year, reaches its minimum around September, and then grows and grows, and then starts heading back down towards its minimum. You can see the whole cycle here from 1980 to 2014. And if you look at the minimum Arctic sea ice around September, compare it from 1880 to the last few years, it's about 1/3 of its value compared to what it was in 1980. And if you just extrapolate, follow your eye along the bottom of the curve down, and you see if you extrapolate with your eye by around 2020, within a few years of 2020, there will be no Arctic sea ice in September. And that will increase the warming of the planet because the ice reflects very well the sun's light that hits it, and the water beneath the ice, when it's exposed, absorbs the sun's light very well. So there'll be an additional contribution to the heating of the planet when that Arctic sea ice melts. And when it melts, of course, it's like 24 hours a day sunlight above the Arctic. Almost done. Here's a graph of the difference in temperature between the North Pole and the equator. The difference in temperature between the North Pole and the equator from 1948 to, I guess 2011. And you see that that temperature difference has been dropping. The last couple of decades it's been dropping. Now the atmosphere is a heat engine. And where all the winds come from, it comes from temperature differences. So there's these jet streams that swirl around the poles, and they kind of isolate the Arctic air from the air like over us. And as that temperature difference drops, because the Arctic is heating a lot more rapidly than the equator, then that heat engine has less energy and the jet stream slows down. And that slowdown of the jet stream allows these big wiggles to form in the jet stream. And so you hear about this thing called the polar vortex, which allows cold air masses to flow from the Arctic down over, for example, us, Michigan. And that's going to happen this weekend. It happened a lot last winter, and winter's just starting, and here it is happening again. So the climate is changing very, very dramatically. We can't keep doing what the speakers at this CCA, told us we had to keep doing. We can't. So there are a lot of people who are thinking of how to get out of this problem. I just have 3 books here I'll just show you, and then I'm done. Oh, I guess I'm not going to show you. Here's one of them. It's called Reinventing Fire by a wonderful guy named Amory Lovins. And he says, you know, fire made us human, and fossil fuels made us modern. We have to find a way to reinvent fire. And that's what this book is about. Thank you.
Lament the fact that the person that I'm replacing isn't here. It's Professor Young in the chemistry department, but I will try to contribute my best. I am a professor of politics here at Hillsdale. My first point is drawn from the Hillsdale student who asked Stephen Hayward, quote, "How do you separate the science from the politics?" My answer is that when science enters the realm of politics, it's no longer science, because politics is the realm of opinion. Politics is the realm of opinion in at least two ways. The first is the most obvious. Do you know the facts? For most of the population, the discussion will remain at the most basic level. Do you believe in global warming? On this level, I wish I could have seen, and think it would have been good for our students to have seen, a roundtable with two climatologists engaged in a scientific discussion about the available data and models, and then perhaps address why they've adopted different political opinions. But even this would perhaps conceal how politics, which couples science to policy issues, immediately distorts sciences. Namely, science becomes a source of authority rather than a mode of inquiry. Science is the quest for the unchanging. Politics is the realm of the changing. The virtue of the first is wisdom, the second is prudence. We've all seen how science is used by politics. Scientists make ambiguous statements, which pundits and media translate into declarations, which politicians respond to and feed more money to scientists who make ambiguous statements, etc. Yesterday, I asked a friend of mine, an environmental scientist who studies climate, for an opinion about popular treatments of climate science. The response was, I quote, "If it's not by science writers, it's invariably crap. I've yet to find someone writing intelligently about climate science," end quote. My second point, when we forget that science and politics have different ends, we start to think we can unite them. Every student here has read Plato's Republic. In that book, the ambitious Glaucon, who longs to see perfect justice, concludes that the best political regime is the rule of the philosopher. Yet the just city that he creates is a place where no one would want to live. It's a tyranny that expels all art, music, and even philosophy itself. Socrates saves the city from Glaucon by directing him away from political life. We find that the greatest impediment to the perfectly just society is precisely the difference between science and politics. The philosopher does not want to rule. The American founders agreed. None but God, they said, was perfectly wise and good. Hence, none but God justly is given absolute power. Standing before a courtroom in 1761, James Otis quoted John Locke's teaching of the limits of the legislature: to rule only by standing promulgated laws, to rule only for the public good and not for a particular class, no taxation without representation, no delegation of lawmaking power to another body. Because men are not angels, the new Constitution of 1787 limited government through separation of powers and checks and balances. The American progressives, rejecting the scheme of constitutional government, believed that the contradiction between science and politics could be resolved. They promised a rule of bureaucratic experts, not unlike Plato's philosopher kings. They would place, via a new science of administration, Socrates on a regulatory board to solve labor disputes and set air ambient quality standards. My third and final point. The rule of the supposed experts in energy policy has led to three great injustices that the Constitution was designed to prevent. First, amidst fanfare at the federal level, Congress in 1970 Clean Air Act delegated its lawmaking power to the Environmental Protection Agency to identify the most important pollutants, promulgate clean air standards, and with state cooperation set in motion their reduction to healthy levels by 1977. But what is the result of the delegation? Few realize that the act was the brainchild of the auto industry, which was searching for a way to minimize its state-level regulatory burden and a federal agency like the EPA that provided exemptions was the best way to do this. Hence, most of the EPA's goals were unmet by 1987 and many by 2007. Congress, under the guise of deferring to the wise experts in the EPA, was able to punt on making the hard moral decision between protecting health and the economy. Congress could take credit for a popular goal, achieving clean air, but leave the means of achieving that end to the EPA. More so, it could blame the EPA when voters complained about the unrealistic cost of its proposed rules, as well as blame the EPA when it had failed to achieve clean air on schedule. Only when voters began to blame Congress did it make the hard, costly choice by passing the Clean Air Act amendments in 1990, which instituted an operating permits program. The states themselves arguably did more to clean up power plant emissions in the 1960s than the EPA accomplished in the 1970s. After the Supreme Court's 2007 decision in Massachusetts v. EPA that the EPA must regulate greenhouse gases under the Clean Air Act, we should expect similar promises and results. The EPA will achieve astounding environmental goals with little impact on the economy. Government, on the one hand, will improve technology and on the other hand, place the burden solely on big business rather than the taxpayer. But the real question is, how much are you personally willing to pay for lower CO2 emissions? And this is not a scientific question, it's a political one. Secondly, the administrative state replaces the rule of law for exception to the law. Because Congress does not pass laws but suggestions today, administrative agencies are given the power of lawmaking, enforcement, and adjudication. According to the progressives, this would allow for flexibility. Experts could apply regulations on a case-by-case basis. This is also Madison's very definition in Federalist 47 of tyranny. Regulations are not promulgated laws. No one can know them. It's not just the sheer volume of thousands of regulations, it's the nature of regulations. The EPA responds more to internal pressures than to the public need for clear laws. The agency defines its powers as broadly as possible and then qualifies its obvious overreach of power by listing a multitude of narrowly defined exceptions. Neither are they standing. They vary so quickly none can keep up. Every business is in violation of some environmental regulation. More recently, even the fiction of law has been abandoned. Michael Grieve, in his article, Administrative Law Without Congress, shows that agencies frequently rewrite environmental and energy laws. Thirdly, regulations are not applied equally. Those with connections are not prosecuted, exempted from regulation, or given special favors. Green energy thrives on such special favors. One need only look at the stimulus and exemptions given to green energy companies, many going bankrupt. Those subsidies grew from $500 million to $5 billion between 2007 and 2010. After issuing global warming rules in January 2011, the EPA exempted a General Electric subsidiary from air quality standards in February. Wind energy is exempted from paying fines for 600,000 birds that windmills kill each year. Under the Migratory Bird Treaty Act, killing just one bird carries fines ranging from $15,000 to $500,000 and prison terms of 6 months to 2 years. Oil and gas companies have large exemptions. Last year, the EPA exempted one oil company, which it did not name, from the renewable fuels mandate. The 2005 energy bill, the so-called, quote, Halliburton loophole, exempted fracking oil and gas companies from 7 major federal environmental laws. Thank you.
Great, thank you. I want to first say thanks to Matt Bell and to the organizers, to my fellow panelists, and especially to you guests and students for attending this conference. I want to look at these issues from an economic standpoint. I'm going to go fast, but I think it's important to note that the two very well-known economists were recently at a conference, became involved in a very heated debate. It was not resolved, and on the flight home, they found that they were seated on the airplane together, one at the aisle, one at the window. And so they resumed their discussion, and after a couple of minutes, the gentleman in the middle said, look, I've been on an international flight for 10 hours. Now I've got 2 more hours. I've got an important presentation to give after we get down, and I'm not getting any sleep. Can I please change seats with you guys? And so one of the economists says, oh, sure, go sit by the window. And so they look at they trade places. The economists look at each other, and one says, you know, that's the first time an economics discussion has kept anyone awake. And now you know why I'm last in the lineup here. At any rate, I want to give a very fast, big picture view as I see it of what we're dealing with here. And one thing I want you to keep in mind as I do is this question: how do free people solve problems? And I'm going to start with some basic facts. And fact number one is that we humans are in a process of building a world civilization. 100, maybe 200 years from now, this is going to be obvious. It may not be obvious now. And I won't predict what it will look like, but I'd be very surprised if it did involve a big world government. I don't think it will. But I do think we'll have an integrated civilization. Second, one of the most important parts of this will be economic development. Right now, the majority of the world's population lives in less developed countries, and they will develop. In fact, they're doing it now. It is happening. Just as an aside, what continent had the highest rate of growth of per capita income last year if we compare Africa and Asia? And the answer is Africa. For the last decade or so, Africa has had per capita income growth of 4 to 6% annually. That's the basket case. So where there is economic growth. Development is a fact, and it will continue, and it will grow. Third, energy production and consumption will greatly increase worldwide, both total and per capita. The two gentlemen from the Manhattan Institute already made this abundantly clear, and they are right. And my fourth fact is that this growth will certainly be accompanied by increases in greenhouse gas emissions. That's inevitable. And again, I think Bryson Mills made that point pretty clear. Now, we can say something about the US-China agreement during the questions and answers. That's maybe relevant here, but there are 4 facts, and the conclusions that I draw from those are, first of all, that development and energy worldwide will increase, and so will greenhouse gas emissions. Great. Well, what can an economist say about this? Let me give some economic analysis. Now, and first, I refuse to offer a professional opinion on anthropogenic global warming, man-made climate change, because that's outside of my professional training. I will simply note that the vast majority of relevant scientists appear to accept it, and they make fairly persuasive cases for it. Economists, historians, etc. should be very careful they should be very slow to argue with physicists about physics. At any rate, I'm going to simply take it as an assumption, or if you prefer, a working hypothesis that the expert consensus is right. And if you reject the hypothesis, that's great, that's fine. I simply want to ask, what if it turns out we're wrong? How would free people solve this problem? So there's the assumption. We're going to assume, at least for the moment, that anthropogenic global warming is true and that it's dangerous. So let me do a little bit of economic analysis. If I say to you, increased energy is good, most of you are going to say yes. And if I'm addressing a climate change conference and I say to them, most of you agree that reduced greenhouse gas emission is good, they will say yes. And you know something? You're all right. So there's a trade-off there, and it would be foolish to maximize one of these things at the expense of, with no regard at all for the other. Both have to be taken into account, is what I would say. If we can reduce greenhouse gas emissions, that's good. But at what cost in terms of reduced energy, reduced income, and reduced human well-being? And if we can increase energy production, that's great. But again, at what cost in terms of a worsened environment, damages, and reduced human well-being? So there's the economic issue, a trade-off. How do you solve the question? And I think economists have about 3 different kinds of, broadly speaking, solutions to this. And the first one is central economic planning. I'm going to just say without explanation that that's to be rejected. And if you want the explanation, you come and you are welcome to take my Austrian economics class next term. Everybody's welcome. We'll explain it. Number 2 is regulation. I'm going to reject that one without explanation. If you want to know why, revisit Professor Grossman's lecture, and Professor Slack just said something about that. And I could say more, but I'll skip that one. What can be done? How do free people solve problems like this? It's a good question. What's the nature of the problem? Well, to an economist, this is a problem that's often called an externality. Well, what is an externality? It's a failure of decision makers to take into account some very important consequences of their decisions. Now, why the heck would they do that? Well, prices communicate costs and they communicate benefits. And for some reason, these benefits that are being excluded are not being considered in the market price. Okay, well, why is that? That could be shown in a long economics lecture that at the root of the problem there is because of incomplete property rights. And at heart, I'm willing to argue all environmental problems stem from this. So what solutions are there? And what do I propose? Actually, I don't propose anything. I will say that there are possibilities. I want to ask, how am I on time right now? Okay, a couple more minutes. I will just say that a number of free market economists have made various proposals that would help better define property rights and give decision makers the right incentives to take things into account. And I can give a couple of examples, but the problem is every one of them has costs and every one of them has benefits. Just an example, Ed Dolan, an Austrian economist and libertarian, has suggested a system under which you'd have strict liability rules for anthropogenic global warming damages. He's argued for this both on from the standpoint of justice, and I mean real justice, not social justice, and also for economic efficiency reasons. Roger Miners, Bruce Yandel, both of them property rights economists, have talked about the use of common law rules for nuisance and trespass and how they could be potentially used in controlling air pollutants and air pollution problems. Greg Mankiw, former chief economic advisor to George W. Bush, has talked about the possibility of taxes on the emissions, that is on the bad part of things, to create incentives. If they're done right, they could work. There are others, and I don't endorse anything. I simply note that there are possibilities for solutions that would improve the property rights regime. All of them have benefits and all of them have costs. Now this is the Ludwig von Mises lecture series, so I think it's now time that we pay a little bit of attention to what Mises said. This is Mises. The decision about any proposed measure is to be made on the ground of a meticulous weighing of the costs to be incurred and the prize to be obtained. No reasonable man could possibly question this rule. So here's my conclusion. What's the bottom line of this? First of all, we need energy. We need development. And we don't want to wreck the environment. We want to find ways to make these trade-offs in such ways that we make things better, not worse. Economics tells us that any time we see a suboptimal situation, such as an externality, it is a potential profit opportunity. If you act on it correctly, you can actually create net benefits. But that means something else. That means that potentially this is not a zero-sum game. Potentially this is a positive-sum game if we approach it correctly. It can potentially be win-win if we approach it right. And that, I think, is why it's important that people on all sides of the climate debate and the other energy issues approach these issues carefully, thoughtfully, respectfully, and especially with a positive-sum mentality. And I know that there are wicked people out there who have adopted climate change, for example, as a Trojan horse for ulterior reasons. And I know there are anti-global warming activists who are simply mindless. But there are also a lot of very good people, thoughtful, reasonable people who I know who are deeply concerned about the climate issue. And they do have that positive-sum mindset. So here's what I think. I think we should be thinking very carefully about what can we say to them about how free people would solve these kinds of problems and get a reasonable trade-off between the two goods at hand. Now, I've got quite a few numbers here to quantify this, but is my time up? Time is up. So this is the end of the economics lecture, so time to wake up.
All right, thank you, Dr. Steele. Thank you for each of the panelists. Now we'd like to open it up, and again, we don't have enough time. but I would love to have as many questions as we can handle in the next 15 minutes or so. So if you do have a question, please raise your hand, and again, the young ladies with the microphones will come to you and wait until they come to ask your question. And again, you can address your question, if you would like, to any particular panelist or just to the panel as a whole. Thank you.
I'd like to thank everybody for coming out today, the professor specifically for speaking to us in this faculty roundtable. My question is going to be for Dr. Hayes. It's going to be talking mostly about the Boulder study and what was the methodology behind that study and why should we prefer it. That's my first half of the question. Second half of the question is what is the role of government in this issue and what can government do to help, or maybe what is the solution to this problem in your mind? Thank you, sir.
The Boulder study of the sea level rise, it's been a series of 3 satellites. It uses a microwave signal that gets sent down, and they time the reflection very carefully. You measure that distance, knowing the speed that microwaves travel. You have to know your starting point very well, so the satellite position has to be known very, very well, and the position of the satellite, its altitude is known to a precision of about 2 centimeters. And you just do that over and over and over and monitor the height of the seas. About the proper role of government, I don't study that. I will not offer any, I don't have any special wisdom. I simply will not answer.
Aside from the fact that Obama, as usual, exceeds his constitutional authority, what use is it to try to curtail CO2 here when all the CO2 increases come from China, India, and the Southeast Asia belt? That's where the increases are. What can we do about that?
Well, again, I think as Dr. Steele mentioned, we're seeing more and more, and I think he would say, although I don't want to put words in his mouth, we're seeing more and more international debate and discussion, and for example, today, you know, some sort of agreement between Obama and the Chinese premier. But I mean, I think it's true that we obviously in the United States can't control what goes on in other countries per se. However, it's also true that the United States, while our rate of growth of CO2 emissions is not, not as bad as it has been in the past, and we're seeing some real improvements with the use of natural gas. I mean, there's still a lot that we can do in this country. Again, not just looking at emissions, but just as our country has done many times in the past, for example, during the Depression, during World War II, you know, when faced with a situation, again, I don't want to call it a crisis, but let's say faced with a situation in which we need to calculate costs and benefits and respond accordingly and do things like, for example, be willing to sacrifice certain desires for certain other longer-term desires. For example, as people were very, proactive in terms of conserving fuel, recycling, doing things like that during the Depression, and then also, of course, during the war years. I mean, there's a lot that people can do that can make a difference in terms of what this country is doing. And again, if we can take away the well, look at the U.S., look how bad they are. I mean, if we can continue to, I mean, we've shown people as a country, we've shown how innovation can lead to tremendous advances in energy development and innovations in lots of different technologies. So it makes sense for us to lead the way, even if, and I won't say this is necessarily true, but even if it were true that we're doing everything right and the CO2 emissions in the U.S. were coming down, and in China and India and everywhere else are going up. Even if that were the case, we would still be setting an example that I think others could follow, which I would love to see us do to at least some extent. I don't know if Charles, you want to address that?
Is this on?
Yeah.
Is it okay? So, a couple of answers or a couple of things I would say. They're not answers. What can we do? Well, first of all, these are international issues by nature. What we're talking about, it's a global issue. But still, ideally, if this is understood properly, it is a win-win situation. It's just very hard to do, but it really is positive sum. Second thing I'd say that international negotiations matter, and so does international trade. Just one thing I would think of, for example, is what about increased trade of technology? It's not in the interest of third world or developing countries to wreck their environments. This is in their interest as well to get problems under control. Technology in the United States is some of the cleanest available. Technology in China is not. Trade that way could actually improve Chinese technology. It's a win-win kind of thing. Something else I'll say, and I was kind of joking about having a lot of numbers, but I do have one that's sort of interesting because World Bank has come out with a study, the economics of adaptation to climate change synthesis report, which is kind of interesting. And one of the things that they talk about, one of their primary recommendation for between now and 2050, they say economic development is perhaps the best hope for adaptation to climate change. Adaptation is important. Second thing they say is that the cost of doing this, and this is a ballpark figure, would be something like $100 billion a year. Potentially it can save maybe, again, these are, I quote these numbers without having studied them, $1 trillion a year in damages. But this is a potential win-win thing, and there's got to be ways to work out deals on these sorts of things.
My question is for Dr. Hayes. In your lecture on Thursday, you stated that 97% of all scientists hold global warming, and then we heard Dr. Hayward reference his the study he found that said that a third of all scientists, 97% of a third of all scientists say that. So just to clear up any of that contradiction, just hear your response on that.
Surely. In my lecture, I showed you a couple of slides. One of them that showed a partial list of national and international scientific organizations that, make statements in support of the IPCC statement on global warming. I also showed you a list of national and international scientific societies that made statements opposing it. And that list was empty. There are none. There have been multiple studies of the fraction of peer-reviewed climate scientists who sign on to the consensus that I presented to you here, just with data. And Naomi Oreskes has done one of the earlier studies, and she also gets 97%. And she does a very different study than Mr. Cook. So the vast majority of peer-reviewed climate scientists accept the story that I presented to you last Thursday.
If I may also respond to that. If you go back, and I don't know if you can listen to Mr. Hayward's talk again, I think, you can correct me if I'm wrong, but I think what he said was that in that particular article, which again was looking at climate change articles, he said that of the scientists who, well, let me back up again. He said, all right, what was the number of scientists who reached an opinion in their article about climate change? And there were, I think, something like 67% of the authors of those articles that were looked at didn't have an opinion, or in that particular article didn't express an opinion, either agreeing or disagreeing with, say, a particular position on anthropogenic global warming. And then he said about 33% of them did express an opinion, and of that 33%, 97% were in agreement with it. So that's where I think you got the figure of a third, was that of the articles, or excuse me, of the references that were looked at in that particular study, only a third were expressing any sort of opinion about the issue that he was of interest to him, and of that third, 97% were in agreement with it. So again, that he's looking at the select articles that were quoted in that particular study, and again, there is nothing there that would suggest that there was a large number of scientists who disagreed with it. It's just in that large number of articles that were looked at, there were quite a few articles that didn't involve expressing an opinion on the subject. Only 33% did, and of that 33%, 97% were in agreement. So, again, it's a little bit, I don't know, disingenuous perhaps, or at least a little bit of the old statistics don't lie, but they don't sit very well. Again, that use of statistics, again, is probably somewhat accurate, but again, it's not giving you a result that is very meaningful, because again, that's simply saying that there were 60-some% of the articles that were referred to that weren't expressing an opinion.
Can I just add a word? Thank you. Thank you. Yeah, so you can publish all kinds of articles involving some aspect or another of climate science where it's not, your result isn't a statement of whether or not you're agreeing with, the general consensus on global warming. It's just some particular detailed measurement you've made, and you don't make any statement, which is what Mark was saying. And that's what those statistics meant. It didn't mean that the people didn't have an opinion. The 2/3 of climate scientists didn't have an opinion on. They were like neutral to the question. It just meant in those particular papers, the issue didn't come up. That's what Mr. Cook meant in his paper. Thank you.
Hi, my name is Gabby. I'm a senior at the college. My question is actually for our two scientists. Now, I understand that the Earth is roughly about 4.6 billion years old, and the data that you've presented today and all the data that I've ever seen about global temperature increases and the oceans rising and things like that have been from the past 50 to 100 years of data, which is, I think we can all agree, a blink of an eye in comparison to 4.6 billion years. And I understand that industrialism has had a huge impact on the environment, that humans have a huge impact on the environment, but is there any evidence to suggest beyond the past 50 to 100 years that this simply isn't, or this is not simply a trend, or that, we're not doomed and that the global temperature won't naturally decrease in the future?
There's all sorts of evidence that extends over much longer periods than just the instrumental temperature record, which I showed today. We didn't get the Earth covered with thermometers with a sufficient density that you could talk about something like the average temperature of the surface of the Earth until about 130 years ago. But there's all kinds of indirect ways you can measure the temperature of the Earth. In my talk last Thursday, I showed you a beautiful way involving drilling holes into the ground and measuring the temperature as a function of depth in that hole. And if the hole has nice properties, the rock is pretty uniform, as you go down you don't run into any big aquifers and rivers and so on underground. You can reconstruct the temperature back 1,000 years, or in the very best hole like 2,000 years. If you dig down in the ice in Greenland, you can go down to about 100,000 years. And you can accurately measure through proxies the temperature where that ice was in Greenland back for about 100,000 years. If you do the same thing in the deeper ice cores in Antarctica, you can go back 800,000 years. So that statement, that the CO2 level that we have today is not been exceeded on the planet for the last 800,000 years. It comes from those ice cores. If you want to go back further, there are other ways involving sediments. I won't spend any more time on it, but there's a lot of data in the past. Now, the Earth's temperature has changed dramatically over the past, and the CO2 concentration in the atmosphere has also changed dramatically over the past. What's unique about this particular change is that it's way faster than anything that we've seen in the record. It's way faster than anything that's happened naturally. And that is a terrific problem for the biosphere because, the biosphere is a very tightly coupled interlocking system. And if things get out of sync, if flowers are blooming before the bees are ready to pollinate them, if all these things don't happen in a nice synchronized way, there's going to be real trouble. And we are in apparently the 6th interval of major species extinction in the history of the planet right now. We're in the 6th one. Yeah, there's been 5 before, and they certainly weren't caused by us. I don't think you would have wanted to live in any of those 5, and you probably aren't going to want to live in the 6th if we don't bring things under control.
My name's Will Crockett. I'm a freshman here. I've got a question for Dr. Hayes. You mentioned that, actually you demonstrated very well that temperatures are rising in the past 50 years or so, and you pointed out that we can see an increase in CO2 levels when we look at ice caps and whatnot. But like you also said, there's been a lot of major temperature changes in the world, including what made the dinosaurs extinct. And I was wondering what evidence you can give us that this one is certainly caused by us and not just another one of those trends. Thank you.
Well, first off, what made the dinosaurs extinct 65 million years ago was the impact of a large asteroid. It had a lot of iridium in that asteroid, and you can dig down anywhere you wish, pretty much, along the surface of the Earth and go down to the layer that corresponds to 65 million years ago, and you can see the iridium layer left over from that asteroid collision. That also wiped out something like 95% of the life on Earth 65 million years ago, and it wasn't due to necessarily immediately to a temperature change. It was due to a large object colliding with the Earth. Maybe you saw the fact that a mountain-sized object passed right near the surface of Mars about 3 weeks ago, at 1/3 the distance between the Earth and the Moon, and NASA had 3 or 4 orbiters and a couple of rovers on the surface which try to make measurements of what happened when that thing passed so close, and there's a long history of that in our own history. So how do we know we're causing it? Well, there's a lot of different ways. One, they're fingerprints. That is, you can try to imagine other things. For example, you can imagine, let's say it's caused by the fact the temperature, the energy output of the sun's going up. Okay? What would you see if the energy output of the sun was going up? Well, you'd see that the temperature during the day was rising, more than it was when the temperature of the sun was cooler, because the sun's energy comes during the daytime and it doesn't come at night. In fact, you see the temperatures at night rising from what they were before. And that's because the CO2 in the air is taking the reflected thermal energy coming off the surface at night and reflecting it back down to keep the nighttime temperatures high. That's an example. And there's a whole set of things you can do to verify, the understanding of what's causing this particular increase in the Earth's temperature. And all works out perfectly.
I think we're going to need to close for the sake of time. However, any of you that would like to are certainly welcome to stay and talk to panelists individually afterward. Thank you very much.